For the second part of Chapter 12, we'll look at Antarctic and Arctic sea ice, the albedo effects, the energy feedback effects associated with that, also clouds. Mountain glacier meltdown worldwide, we'll look at how mountain glaciers are melting overall. And finally, ocean temperatures and sea level rise, which a great component is the meltdown of those continental glaciers, but also looking at thermal expansion too. Arctic sea ice has declined about 40% since 1958, about 10% loss per decade. It is accelerating over time. The Northwest Passage first opened in the summer in 2007, and this is a passage where you could conceivably get through with a ship across the northern part of North America. Predictions are for ice-free summers by about 2020 or 2030, depending on which model runs you're looking at. This is looking at 2016, August 9th, the opening of a Northwest Passage then. Again, you could conceivably get through here with a boat. Sea ice is typically thicker in the Arctic than it is in the Antarctic. Why is this the case? Two primary reasons. The Antarctic sea ice forms closer to the equator that we'll look at. The Arctic sea ice is more trapped by the geography and tends to converge, making thick sea ice ridges. Here you can see a sea ice ridge kind of accumulating on itself as it converges. It's bounded by continents, so it tends to cluster together. However, it also can grow directly at the North Pole, which is a place where you can have a minimum amount of sunlight over the course of the year, so that's a good place to promote ongoing sea ice throughout the year by growing it right at the pole. That's not allowed to happen at the South Pole. Here, looking at the seasonality of the Northern Hemisphere sea ice, they typically look for the maximum extent of frozen sea ice in March at the end of the long, cold winter. And so you can see it's bounded by continents. It's only so far you can grow it. And in September, the end of their long, hot summer, this is the minimum extent. You still have, on average, a decent amount of ice because it's simply in an area with the least intense sunlight. Yes, they have 24 hours of sunlight here at that time of year throughout the summer. However, it's coming in an extreme angle, so the solar flux is not that pronounced. The Southern Hemisphere sea ice, at the end of their warm summer, not a lot of sea ice at all, and this is because it had to form at closer to the equator than the Arctic sea ice, so there's a chance the sunlight to be intense throughout the summer on those edges of the continent and melt out that sea ice. Also, whatever sea ice fractures out can easily mobilize and move off to other latitudes, whereas this sea ice is trapped from doing so in the Arctic region. At the end of their long, cold winter, however, in Antarctica, first of all, it's very cold there, and also it's not bounded by a continent, so it can grow as far as it wants as long as the temperatures are cold enough to freeze that seawater. You have no bounds on the sea ice extent there. We can look at this distribution kind of hemispherically averaged. The northern hemisphere looking at the Arctic sea ice averaged over time in blue, the southern hemisphere in black, and looking at these oscillations of total area of sea ice in meters squared. So the first thing to look at is that almost all of the southern hemisphere ice is gone at the end of their summer, and this again is because the ice further from the pole, the sunlight's intense enough to start to melt it, but it also can mobilize away from that area. Any kind of active storm can break off sea ice, and off it goes into the Southern Ocean. Lots of ice remains in the Northern Hemisphere winter, closer to the pole, and it's also trapped geographically, so they'll still have a decent amount of ice in the Northern Hemisphere at the end of their summer. And then finally, huge amounts of ice build up around Antarctica because it's not geographically bound. It can grow as far as it wishes as long as it's cold enough, but there is a limitation on how far you can get sea ice to grow in the Arctic region, the blue line. More pronounced seasonality of sea ice in the Southern Hemisphere than the Northern Hemisphere for those reasons. This graph looks at the Arctic in blue and Antarctic in red, standardized anomaly and trend. So they're taking an anomaly from some average from 1981 to 2010, and then looking at the trend of that anomaly over time. You can clearly see that the Arctic sea ice has been declining over that time, and you can also see that the Antarctic sea ice has been increasing a little bit over time, so that's an interesting effect. So the Arctic's loss is likely due to high warming rates. It could be storminess too. You get storms that come in there and break up ice, and they're actually pretty good at doing this too, but high warming rates are definitely a factor here. And the Arctic loss is about 3 times that of the Antarctic gain. Now there's 3 competing theories about why Antarctic sea ice is actually increasing a little bit over time. The first is higher winds due to pressure anomalies, perhaps tied to something happening with the ozone hole. The second theory is the freshening of surface water from continental melt. As you melt the continental ice, that freshens the surface water, that raises the freezing point of that water, makes it easier to freeze. The last theory, more snowfall in the Antarctic region, helps promote sinking of thin ice. So you put a little bit of weight on the thin ice and it sinks down. That snow easily takes in seawater as it absorbs it, as it kind of sinks with that thin ice, and it allows it to flood into that sea ice and then refreeze it, making that sea ice thicker. So all those processes are a little bit different. It could be some combination going on there, but one thing is 100% clear. We are directly measuring warming for Antarctica. So it's not that Antarctica is getting colder over time. There are just some interesting processes here that are causing sea ice to grow somehow. If you go to my notes, you can look at this link and get a lot more information on those processes. I would like to point out one more proposed mechanism for how Antarctic sea ice is growing that makes sense to me. A more persistent thermal low, so the oceans are definitely warming here off West Antarctica. Warm anomalies, as we found out chapters ago, promote low pressure systems. And around low pressure systems in the southern hemisphere, winds rotate clockwise. And as that drags that continental air down to the Ross Sea, that's extremely cold air that could help freeze sea ice. So there's all kinds of dynamic mechanisms that could be promoting sea ice formation overall. And the Ross Sea specifically is an area where the sea ice is definitely growing. So again, we're measuring Antarctic temperatures on average as warming. However, the sea ice is growing. There must be some interesting processes going on to make that happen. In addition to Arctic sea ice having less aerial coverage, the area of the sea ice decreasing over time, it's also getting less thick over time. And we've measured this for a number of years from submarine, but also we have instruments on satellites called IceSat that can measure directly the thickness of the sea ice too. Taking kind of an annual average, this is looking at summer versus winter, these two lines, but taking an annual average in the between them from about 3 meters thickness on average for the Arctic, going down now to half of that, 1.5 meters thick. Now the ocean loses heat to the atmosphere about 100 times faster from the open water than it does through the insulating ice cover. So ice is a significant insulator at the average thicknesses you see in the Arctic. If you remove it, heat exchange is much more pronounced. So this picture is just a dramatic way of showing that when you do open up leads, which are openings in that sea ice shield, you do get a bigger exchange. Typically here, the Arctic oceanic water temperature is higher than the overlying atmosphere. Heat exchange always goes from hot to cold, so you're seeing heat go, especially during the wintertime, from the warm ocean to the cold atmosphere. So in general, the more sea ice you can remove, either by leads or storms or by melting it over a period of decades, the more heat exchange you get from the ocean to the atmosphere in the Arctic. Sea ice affects the albedo and it insulates the ocean from the atmosphere. Long, straight openings are called leads in the Arctic ice pack, but also you have polynya, which are more pronounced kind of circular openings. In either case, you're going to get more heat exchange going from the ocean to the atmosphere, but also this promotes more sea ice formation if it's cold enough. So there's only so much sea ice you can grow until it's all sea ice. If you can crack a hole in the ice, you can promote more sea ice formation. So in other words, you can freeze more freshwater component the more openings you have, which is going to promote the salinity around there and really promote the bottom water formation. And again, these leads are opened up by natural processes like storms or currents or even Coriolis effect turning parts of the ice. In general, over time, we're seeing a decrease in thickness and spatial extent of Arctic ice, so allowing more heat to come out of the oceans, heating the atmosphere of the Arctic, which is part of why the Arctic is warming at 3 times the rate of the rest of the globe. Summarizing the effects of ice in the Arctic. Consider the surface with ice compared to open ocean. The albedo of ice is higher, so there's going to be less shortwave or solar energy absorbed with more ice. The temperature of ice is lower than the liquid ocean, so there's less sensible heat flux to the atmosphere. Lastly, it's harder to sublimate ice, go directly from solid to gas, than evaporate water going from liquid to gas. So there's less latent heat flux to the atmosphere if you have an ice sheet on top of the water. So in these 3 primary ways, sea ice acts to insulate the atmosphere from the ocean. Recall, both the atmosphere and ocean transport heat poleward. The sea ice thus stops the ocean from exchanging that heat once it gets all the way up into the northern zone. So when there's sea ice, the Arctic stays relatively cold. When there's no sea ice, the Arctic can stay warmer because the ocean promotes heat of the atmosphere. This is the sign of a positive feedback. So let's see how this feedback works. If temperatures get colder, then there's more sea ice, less open water. Then there's less heat flux from the atmosphere to the ocean to keep the Arctic warm, so it gets even colder. So that's a positive feedback loop promoting cold temperatures. However, you can run it the other way too. If temperatures get anomalously warm, there's less sea ice or more open water. That means more heat flux to the atmosphere from the ocean, promoting warmer Arctic temperatures. Now here's looking at an ice core from Greenland that goes back about 100,000 years. Again, they're looking at the isotopic composition in the ice to infer temperature. And what they show in Greenland are very quick oscillations. And these are not oscillations in tune with Milankovitch cycles. These are much quicker, much more rapid oscillations in temperature in the Greenland ice core. Rapid transitions from one climate to another are very symptomatic of positive feedbacks. So you need some positive feedbacks to really amplify any small change in temperature. The climate change near Greenland is closely linked to Arctic sea ice. So the Arctic sea ice is a very sensitive mechanism, and it definitely provides positive feedbacks in the climate system. Right now, it's probably a huge feedback as far as promoting the Arctic atmosphere from getting 3 times the amount of warming we've seen globally. Now, the effect of clouds is on the cutting edge of what's happening here, because you want to figure out if you have more open water, you're going to have more evaporation happening, more water vapor to condense in the clouds, so maybe you'll get more clouds. So that would represent a negative feedback where heating all of a sudden opened up more water spaces, but you got more evaporation and more clouds, which cooled the area down, so stabilizing the temperature. However, in the Arctic region, the sun's only out for a given period of time during the summer. Most of the year it's quite dark there. Therefore, if you have those clouds there then, they're mostly just trapping infrared radiation near the surface. So that would represent another positive feedback, helping to promote at least the lower levels of the Arctic atmosphere heating over time. So disentangling the importance of both those effects is something that's actively being studied, and here's a link to a NASA study looking at that. Switching gears to mountain glacier meltdown, most mountain glaciers are melting. In Asia, enough melt that new lakes are formed by the hundreds. They could flood over and they're very unstable. In Africa, the equatorial mountains, Mount Kenya, Kilimanjaro, and more, have lost more than 80% of their ice. And now there's lots of political conflict fighting over the meager water that's now coming from those glacial areas. Europe and America's melting glaciers in general. These two graphs, this first one's looking at the number of observed glaciers. Doesn't mean the number of glaciers total, it just means the ones we're keeping track. So over time from 1946, we were hardly looking at any of them, and now over time we're really looking at a number of different glaciers. This graph on the right looks at the glacier mass balance. There's a straight line down the middle, everything to the left of that line is melting out, and everything to the right is growing a little bit. You can clearly see that most glaciers are melting. Kilimanjaro in 92 versus 2005, 92 on the left, 2005 on the right. Peer-reviewed research suggests that this is mostly land degradation and not global warming. What the study showed specifically was that the communities around the base of Kilimanjaro have cut so many of the trees down that's limited the amount of evapotranspiration, which limited the amount of water vapor, and ultimately that limited the amount of fuel you can get as orographic precipitation on the top of the mountain. Looking at the oceans, again, sea surface temperatures are rising in pretty much all the oceanic basins. Warming of around 1 degree Fahrenheit from the surface to around 10,000 feet in depth. This represents an enormous storage of energy since the oceans have such high heat capacity. When that energy is returned, it will ultimately raise atmospheric temps back up by 1 degree Fahrenheit. This would be on top of greenhouse gas warming at that time. Essentially, greenhouse gases right now are charging the oceanic battery, which will give power or heat back to the atmosphere at some point. The deep oceans therefore give the climate system high thermal inertia, but you can't sweep the problem underneath the mat forever. Eventually, the ocean circulation will give the heat back to the atmosphere. This graph shows just this. The excess radiative energy generated by greenhouse gases is mostly going into the oceans. So here they're showing the energy in zetajoules, time from 1970 to 2012 about, and they're showing how much went into the land, a little bit as the gold, how much went into melting ice or into the ice, a little bit as the white, how much went in the atmosphere, very small fraction as the magenta here, and how much went into the upper ocean, the light blues, to the deep ocean, the deep blues, and a lot, right? So most of the energy is going into the oceans and not affecting the atmospheric temperature right now. How long the ocean can sequester that heat is up to the oceanic circulation. So thinking about this, why would El Nino years tend to be warm? So El Nino years are the time when The Central Pacific has a huge covering of relatively warm water. That would represent a huge sensible energy flux from that warm oceanic water to the atmosphere above it. So this is a time when the ocean's actually giving a lot of heat to the overlying atmosphere. So looking at the data, you can see 1998 was one of the strongest El Niños ever. Global average temperatures, this is land and ocean temperature anomalies, very high. And then again in the last big El Nino in 2014 roughly, another year of very high atmospheric temperature. So again, during El Ninos, huge part of the Pacific Ocean is covered with warm water that gives a lot of sensible heating to the atmosphere. So you'd expect the atmosphere at that time to be quite warm, and they are. They are. El Nino's years are warm for that reason. The ocean's just not taking as much heat in as it usually does because it's relatively hot at the surface, high sea surface temperatures. Changes in sea level during the 20th century. There's good agreements between tide measurements, reconstructed sea level fields, and satellite altimetry. 20 centimeter rise from about 1900 to 2000. Most of this rise was due to mountain glacier meltdown and also thermal expansion. Water, as you get it warmer, expands, so it takes up more volume. This graph looks at potential problems in the future, looking at Greenland ice sheet. If you melted that, it would raise sea levels 8 meters, West Antarctica 6 meters, East Antarctica is about 65. The combination of west and east is about 70 meters total. Thermal expansion, warming the water, it takes up more volume, so it could increase sea levels by up to about 3 feet. Here's looking at a scenario, flooding, basically melting the entirety of all our ice caps and seeing what would happen globally. So we're looking at Florida and Louisiana, well up the Mississippi flooded. Also a huge proportion of the Amazon, parts of Patagonia, huge parts of Europe, large parts of Indonesia, as well as parts of China too. Here's a very important region too in Bangladesh as well. So those are doomsday scenarios and they're worth looking at. However, who is at risk right now? These are places called low elevation coastal zones, places that are well populated and are less than 10 meters high right now. Bangladesh and Vietnam are two very highly populated low elevation coastal zones. New York City, Boston, and Miami as well. Miami has problems right now with sea level rise, and they're expected to have more problems in the future. The Netherlands is one region where it is taking action over reducing the amount of flooding, and you can look at more information from that link. To the nature of the slope of the coastlines, if these places must retreat from sea level rise, 1 meter of sea level is about 1 kilometer of retreat. So a pretty significant amount of people would be displaced with 1 meter sea level rise. And looking at the US, you can see that the entire southeast coast is pretty much a low elevation coastal zone. So if sea level comes up significantly, this is going to be a major problem for the East Coast. So those low elevation coastal zones will see a problem very soon. However, what's the most eminent economic threat to low-lying island nations with regards to sea level rise? So this is happening now. It's been happening for 10 years or more. Is it erosion of high-dollar real estate, saltwater encroachment into water supply and agriculture, destruction of coral reef, habitat loss for plants and animals? Obviously, all of these are happening, but the one that's most important right now is that saltwater encroachment into the water supply and agriculture. An example is what's happening in the Maldives. Here's their capital, Male, and they have protected themselves with a seawall around the capital to help combat storm surge. So obviously there's gaps in here where they have boats that come out here, so sea levels can rise up here. However, this knocks down the big waves. That's part of the surge associated with storms that come on top of sea level rise. So the most eminent threat for them right now is seawater contamination of their underground fresh water. From a recent study, the freshwater table sits just a meter or two below ground in the coral that makes up the islands, just inches from seawater below and human waste above. The proximity of groundwater to the surface and the porous nature of the sandy soil make it highly susceptible to pollution and contamination from human activities and saltwater intrusion. So basically their groundwater is getting contaminated from the top and from the bottom. So what's happening with them? Well, they're harvesting rainwater right now. Donations have given them tons of rainwater buckets. Luckily, they're in a zone where they get enough rainwater that can help them substantially. They also have some desalination machines in use. These things are generally prohibitively expensive. However, they do have a number of them from donations around the globe. And also environmental education is helping them as well. On top of those problems, they're also seeing some bleaching of their reefs, which they depend on for fishing and also tourism. So we can look at bleaching later, but this specifically, a lot of times bleaching is related to enormously high sea surface temperatures, so you can correlate it to global warming as well. So the latest IPCC scenario projections for sea level rise, we see that the RCP 8.5 gives us 1 meter total sea level rise from about the beginning of the Industrial Revolution. Again, we went up about 20 centimeters till about the year 2000. They're predicting another roughly 0.8 meters sea level rise on top of that. The RCP 2.6, which as a reminder is the optimistic view that our maximum amount of CO2 happens at about the year 2050, and then we start scrubbing out more CO2 than we release at that point, bringing down CO2 concentrations. It's interesting to compare and contrast these scenarios. Obviously, the less CO2 we can emit, the less sea level will rise as a result of global warming, and there's a pronounced difference here between these two, roughly 0.3 meters or so different sea level rise. However, they're maybe not as far apart as you might have thought. So it seems that we've already set the stage pretty well for sea levels to rise significantly no matter what we do. That shouldn't be taken as an excuse not to do anything, however, because there is a big difference between the future scenarios here. And also you can see that the slope of the line here for the 8.5 scenario is drastically increasing upwards. As you go another 20 years or so beyond this, the difference between the two scenarios will be much more pronounced. So at the same time, we've already set ourselves for some amount of sea level rise in the future. We have to be clear that making better choices about fossil fuel usage is going to lessen the effect for these low elevation coastal zones, and so any kind of mitigation we can do is worthwhile. And we also have to keep in mind that neither scenario really considers any of the nonlinear ice feedbacks that we looked at in Greenland or West Antarctica. Key points for Chapter 12, Part 2. Sea ice in the Arctic is on the decline, and it's a large positive feedback for future warming. Mountain glaciers are melting fast, and they won't have a big impact on sea level rise in the future because we don't have that many mountain glaciers left to do that. However, they're important for drinking water and a variety of other purposes, so it's important that they are melting fast here. Sea level rise impacts are expected to be large in the future, mostly due to the projections of Greenland and West Antarctic melting. A lot of this sea level rise is already put in play by the warming we've already experienced. However, mitigation policies will be important in limiting the amount of sea level rise that actually happens in the future. The most eminent effects today are for low-lying nations that are seeing saltwater encroachment into their drinking water and the areas that they actually use for agriculture.